So in a lecture 4, we discuss one dimension heat equation problem number 2 and its example. That means lecture number 2, lecture number 3 and lecture number 4 based on one dimension heat equation, type of the problem and its example. Now we discuss a one dimension wave equation. So basically in this type of problem we consider a elastic string of length L which is stretched tightly between two fixed points x is equal to 0 and x is equal to L with uniform tension T. Again, we consider an elastic string of length L which is stretched tightly between two fixed points x is 0 and x is equal to L with a tension T. Displace it slightly from its initial position of rest and release. Then obviously the string will vibrate. Therefore, the problem is to determine the displacement or deflection U. Displacement and deflection U at any point on the string at any time t from the origin. Its displacement is given by the function uxt and the equation of motion is defined del square u by del t square. That means the wave equation. Del square u by del t square is equal to c square del square u by del x square, where c square is t upon rho. Now we discuss a boundary condition and initial condition of this problem. So first, boundary condition. So here the string is fixed at two ends, 0, x is equal to, and x is equal to L for any value of t. So we get two boundary conditions. First, u0t, where the distribution, that means displacement, initial displacement uxt is 0 and ult is also 0. That means ends is a fix at x is equal to L. So boundary condition, when x is 0, u is 0. When x is L, u is 0. Now initial condition. So the motion of the string depends on the initial deflection fx and initial velocity gx at the time t is equal to 0 at the point P. Thus, we have two initial conditions. One, ux0 is fx, which is called initial displacement, and utx0 is equal to gx, which is called initial velocity. So the whole problem, one dimension wave equation with two boundary condition and two initial condition. Now there are different types of a one dimension wave equation, and we consider three part. That means the problem 1, problem 2 and problem 3. Problem 1 is based on only initial displacement is given, initial velocity is 0. Another, all things are same. That means the boundary condition is similar for all problem. Only the initial condition is changed. So first problem, only initial displacement is given, velocity is 0. Problem 2, only initial velocity is given, displacement is 0. And problem 3, both are given. So now we discuss a problem 1. So problem 1, when only initial displacement of the string is given. So therefore, the initial boundary value problem of this type of concept, we write one dimension heat equation. So equation 1 with the boundary condition u0t is equal to 0 and ult is equal to 0, because the length of the string is L. So equation 2 and 3, boundary condition and initial condition. So only initial displacement is given. So we write ux0 is some function fx. And velocity is 0. So utx0 is 0. So 4 and 5 is the initial condition. So now we solve this type of problem. So first we solve equation 1 using separation of variable method. So in a previous lecture also we discussed how to solve any PDE using the separable variable method. So similar procedure. Let us consider the solution form uxt is equal to capital X of x, t of t, because u is a depends on x and t. So first we consider uxt is equal to x of x, t of t. Differentiate equation 6 2 times with respect to x and t. So we get del square u by del x square is equal to x double dash t, and del square u by del t square is equal to x t double dash, where x double dash is a d square x by dx square and t double dash is equal to d square capital T by dt square. Now we input both value in a equation 1. Then the given PD is reduced, xt double dash is equal to c square x double dash t, and which implies we write x double dash upon x is equal to t double dash upon c square d, which is called equation 7. So in equation 7, the given PD becomes OD. And it is also seen that left hand side of equation 7 is a function of x, right hand side is a function of t only, left hand side is equal to right hand side for all value of x and t. So we consider both sides is equal to the constant k. So we get 2 ODE, ordinary differential equation, like x double dash upon x is equal to k and t double dash upon c square t is equal to also k. Now both ODs are second order, so we consider the different case of the value of k. So first we consider k greater than 0. So let k is equal to p square, because p square is always greater than 0, p not equal to 0. Then the two ordinary differential equation obtained as k is p square we input in equation number 8. Then we get x double dash minus p square x is 0. So this is the second order OD we solve. So the auxiliary equation is m square minus p square is equal to 0. Therefore m is equal to plus or minus p. And plus or minus p, that means real and different roots. So we write the solution form is x of x is a c1 e raised to px plus c2 e raised to minus px. Similar way, T double dash minus C square P square T is equal to 0. This is again the second order ODE. So the auxiliary equation is M square minus C square P square is 0. Therefore, we write M is equal to plus or minus Cp. This is again the real and different root. Therefore, T of T is a C1 e raised to Cpt plus C2 e raised to minus Cpt. So we write the solution form uxt for the case k greater than 0 is x of x t of t. So C1 e raised to px plus C2 e raised to minus px, C3 e raised to cpt plus C4 e raised to minus cpt. So equation number 9. Here we write C3 and C4, not C1 and C2. So all are arbitrary constant. So equation 9 is the solution form for the k greater than 0. We apply the boundary condition equation 2 in equation 9. U equal to 0 when x is 0. We get 0 is equal to C1 plus C2 because e raised to 0 is 1, e raised to 0 is 1. So C1 plus C2 and the another term C3 e raised to CPT plus C4 e raised to minus CPT is similar. That implies this is nothing but T of T. So T of T. So that implies T of T never 0. So we write C1 plus C2 is 0. Therefore C1 is equal to minus C2. Now we input C1 is equal to minus C2 in equation number 9. Then the equation 9 becomes uxt is equal to C1 e raised to px minus C2. C2 is replaced with minus C1. Therefore C1 is common. So e raised to px minus e raised to minus px. C3 e raised to cpt. C4 e raised to minus cpt is similar value. So this is equation number 10. Now we apply the second boundary condition u equal to 0 when x is L in equation 10. So we get 0 is equal to C1 e raised to PL, x is replaced with L, minus e raised to minus PL, and the another remaining term C3 e raised to CPT plus C4 e raised to minus CPT is similar. That implies 0 is equal to C1 e raised to PL minus e raised to minus PL into T of T. Now this value is indicate T of T is not equal to 0. In this equation, T of T not equal to 0. PL also not equal to 0. Then this term is also not equal to 0. And we can't consider C1 equal to 0 because we consider C1 is 0, then C2 is 0. And C1, C2 both are 0, then x of x is also 0. So that means we conclude that the non-trivial solution of equation 1 does not exist which satisfy the given boundary condition. Here, not equation 10, equation 1. So, for the case k greater than 0, the non-trivial solution not exist which satisfy the boundary condition. Now next, case 2, we consider k less than 0. So k less than 0, we write k is equal to minus p square, where p not equal to 0. Then the given to ODE obtain as x double dash plus p square x is 0. Now this is second order ODE, so auxiliary equation is m square plus p square is 0. So m is equal to plus or minus pi. A complex root. So we write C1 cos px plus C2 sin px. Similar, we apply here the same concept. T double dash plus C square P square T is 0. So the auxiliary equation is m square plus C square P square is 0. Therefore m is equal to plus or minus Cpi. So again this is the complex root. So we write T of T is a C3 cos CPT plus C4 sin CPT. So for the case k less than 0, the solution of equation 1, we write uxt is equal to c1 cos px plus c2 sin px, c3 cos cpt plus c4 sin cpt. That c1, c2, c3, c4 are arbitrary constant. So now we are applying the boundary condition equation 2. U is 0 when x is 0. In equation 11, we get 0 is equal to c1 cos 0 is 1, c2 sin 0 is 0. So we write only c1, and this term is similar because this term is not a depends on x. So that implies 0 is equal to c1 into t of t, where t of t not equal to 0, so we write c1 is 0. So we input c1 is equal to 0 in equation 11. Then 11 become uxt is a c2 sin px, c3 cos cpt plus c4 sin cpt. We call equation 12. Now in equation 12, again we apply the boundary condition equation 3 when u is 0, x is equal to L. So we get x is replaced with L. So 0 is equal to c2 sin pl. When x is equal to L, u is 0. So 0 is equal to c2 sin pl, c3 cos cpt plus c4 sin cpt. That implies 0 is equal to c2 sin pl. This is t of t. T of t not equal to 0. We can't consider c2 equal to 0 because c2 0. Therefore x of x is 0. So we consider sin pl is 0. Sin pl is 0, so pl is n pi, and that implies p is equal to n pi by L. And hence we can say the solution of equation 1 satisfied the boundary condition. And we get uxt is equal to c2 sin n pi x by L. We replace p with n pi by L. So we get the equation number 13. Now in equation 13, we are applying the initial condition, equation 5. Equation 5 is a initial condition for the initial velocity. And the initial velocity equation is utx0 is 0. So obviously, first we differentiate uxt with respect to the time t. So for that, we differentiate equation 13 with respect to t. We get utxt is equal to c2 sin n pi x by L, and we differentiate this term with respect to the time t. So minus c3 cn pi by L sin cn pi by L into t plus c4 sin derivative is cos into cn pi by L. So equation 14. In equation 14, we apply the boundary, initial condition utx0 is equal to 0. We get 0 is equal to c2 sin n pi x by L into c4 cn pi by L, and that implies c4 is 0. So c4 is 0, we input in equation 13, we get uxt is equal to c2 into c3, we consider bn, so bn sin n pi x by L cos cn pi by L into t, where n is 1, 2, 3 up to n so on. So we applying the superposition principle, the solution form which is satisfied the boundary condition and one initial condition, we write uxt is equal to summation n is 1 to infinity bn sin n pi x by L cos cn pi by L into t. Now we consider k equal to 0 case. So k equal to 0, we input in an equation 8. K equal to 0 here, k equal to 0 here. Then we get two OD, x double dash is 0 and t double dash is 0. So x double dash is 0, so we write m square is 0. So m is 0 two times. So the solution is a C1 plus C2x. Here the solution form is a C3 plus C4t. So we write uxt is equal to C1 plus C2x, C3 plus C4t. So equation number 16. So equation 16 is the solution form when k is equal to 0 case. Now we apply the boundary condition equation 2, u is 0 when x is 0 in equation 16. We get x is 0, u is 0. So 0, C1, C3 plus C4t implies C1 into T of t. So C1 is 0. We got T of t not equal to 0. And C1 is 0, we input in equation number 16. Then 16 become uxt is equal to C2x, C3 plus C4t. Equation number 17. In equation 17, we apply a boundary condition equation 3. When x is L, u is 0. So 0, C2L, C3 plus C4t. Where T of t is not equal to 0, L not equal to 0, and we can't consider C2 is equal to 0. If we consider C2 is 0, then x of x is 0. Hence, the non-trivial solution of equation 1 does not exist for k equal to 0, which are satisfying the boundary condition. So for k greater than 0, non-trivial solution not exist. K equal to 0, non-trivial solution not exist. So only the case k less than 0, the non-trivial solution is exist, which satisfy the boundary condition and initial condition. So thus only one solution occur in equation 1, satisfy the boundary condition 2 and 3 and initial condition 5 is given by uxt is equal to summation n is 1 to infinity bn sin n pi x by L cos c n pi by L into t. Now in equation 18, we apply one remaining initial condition, equation 4. And equation 4 is a initial displacement. When t equal to 0, we consider the displacement is some function fx. So we apply this condition in equation 18, we get fx is equal to summation n is 1 to infinity, because when t is 0, u is fx. So fx is summation n is 1 to infinity bn sin n pi x by L into cos 0 is 1. So this is equation 19. Equation 19 is a half range sine series expansion of fx in the interval 0 to L, where the Fourier series coefficient Bn is defined as Bn is equal to 2 by L integration 0 to L fx into sin n pi x by L dx, where n is equal to 1, 2, 3 up to and so on. So the solution of the problem 2 is equation 18, where we consider Bn is 2 by L 0 to L fx into sin n pi x by L dx. Now we discuss one example based on the problem 2. So a tightly stretched string with the fix and x is equal to 0 and x is equal to L is initially in a position given by uxt is equal to u0 sine cube pi x by L if it is released at the rest from this position. Find the displacement uxt. So in this problem, given that the length is L of the string, also given that the initial displacement is u0 sine cube pi x by L and initial velocity is 0. Therefore, the initial boundary value problem is given as one dimension heat equation with the boundary condition equation 2 and 3, and the initial displacement is a u0 sine cube pi x by L and velocity is 0. So the solution is, so this problem is similar to a problem 1. Therefore the solution form is uxt is summation n is 1 to infinity bn sin n pi x by L into cos cn pi by L into t. So in this solution, we are applying the initial condition 4 on equation 6. The condition 4 is ux0 is equal to u0 sine cube pi x by L. So u0 sine cube pi x by L is equal to summation n is 1 to infinity bn sin n pi x by L into cos 0 is 1. So we get this form. So actually we find the value of bn using the formula 2 by L into integration 0 to L fx into sin n pi x by L dx. But here left hand side, that means the initial displacement is in the form of sine, and we know that what is the formula for sine cube pi x by L in the form of sine x and sine 3x. So directly we compare and then we define the solution. So first we expand sine cube pi x by L, so u0 by 4 3 sine pi x by L minus sine 3 pi x by L, because we know that sine cube x is a 1 by 4 3 sine x minus sine 3x. So using this formula we write this form, and in the right hand side we expand n is 1, n is 2, n is 3 up to and so on. So n is 1 to infinity bn sin n pi x by L. So in the left hand side and the right hand side, the both form is based on the sign. So we compare both, then we get b1 is equal to 3u0 by 4, b2 is 0, b3 is a u0 by 4 but minus, and another all term b4 b5 up to and so on are 0. So here b1 n is 1, so b1 sine pi x by L. Here 3 u0 by 4 sine pi x by L. So sine pi x by L, the coefficient is a 3 u0 by 4. So b1 is this, b2 similar 0, and b3 is minus u0 by 4. And another remaining term b4 b5 b6 up to and so on are 0. So we input b1 b2 b3 up to and so on here, then we get uxt is equal to u0 by 4 b1, so u0 by 4 3 sine pi x by L into cos c pi by L into t minus sine 3 pi x by L into cos 3c pi by L into t. So equation 7 is the solution of the given example. So now, thank you very much. I complete lecture number 5, which is based on the one dimension wave equation, problem number 1. In the next lecture, we discuss the problem 2 and problem 3 and its example. Thank you.